Welcome everybody for the course Quantum Field Theory for Cosmology. I will start with a bit of a historical overview, and then I will go into the two branches of quantum field theory, and I will explain which one we will take. So historically, the situation is this. In about the year 1900, classical mechanics became experimentally untenable. There were clearly contradictions to classical mechanics. In particular, black body radiation had become a problem. It was so much of a problem that it was called the ultraviolet catastrophe. The ultraviolet catastrophe was the fact that if you assume the Maxwell equations and use ordinary thermodynamics, then the prediction that follows is that a black body will radiate with a spectrum that has more and more intensity the shorter the wavelength. So in fact, the prediction would be that any object would immediately radiate off all its heat in an instant, because the intensity of the heat radiation would be infinite. The shorter the wavelength, the more energy is radiated. That was the prediction, and obviously that was wrong. The intensity of the black body radiation, the heat radiation, does go up initially with diminishing wavelengths, but then it drops down again, and so overall it is of course finite. This was resolved by quantum theory, and then the photoelectric effect was found also at around the turn of the century, and that was a striking phenomenon. It was the phenomenon that if you want to use radiation to ionize a metal, then whether or not you succeed has nothing to do with the intensity. If you can't ionize a metal, then increasing the intensity of the light won't help. Only increasing the frequency does. That was eventually resolved by Einstein, who figured that really photons are at play here, and the question is whether or not a photon has enough energy to ionize an atom to get an electron out of its orbit. And more intensity of the light only meant more photons, but didn't mean that the individual photons suddenly had more energy available. So that required quantum theory to be resolved. This is, by the way, what Einstein got the Nobel Prize for. And then there was this curious phenomenon that matter was stable. And according to classical mechanics, it really shouldn't. They understood at around the turn of the century that atoms are a bit like solar systems, with electrons orbiting nuclei. But if this was so, then unlike solar systems, these atoms should not be stable. And the reason is that, as had been known since Maxwell, accelerating charges are radiating off energy. So if electrons were indeed orbiting atoms, then because they were accelerated, going not in a straight line, they ought to radiate off energy. And that they do. If you take an electron here and a nucleus there, and you let it loose, it will fall towards the nucleus and will start orbiting in tighter and tighter orbits while emitting photons in the process. But eventually it will settle in a stable orbit. Now we understand why that is. It's basically because of the uncertainty principle. The electron will fall down to smaller and smaller orbits until it's localized so much, until its delta x, its position uncertainty, is so small that by the uncertainty principle, the delta p that it has is sufficient to make it escape again from the nucleus. so that it doesn't have to fall in, or in fact cannot fall in any closer to the nucleus. The smallest Bohr radius is indeed what the uncertainty principle gives you. So what we have is that the uncertainty principle was needed to explain the stability of matter. Now, they didn't have it just yet at 1900, but this was just the beginning of the crisis, and then eventually it was resolved in 1925. This is when Heisenberg discovered non-relativistic quantum mechanics. What had been done previously was just piecemeal. Einstein didn't really have quantum theory, and with the explanation of the photoelectric effect through photons. And Max Planck also didn't understand quantum theory yet when he postulated that radiation can only be coming in packets. Also, the uncertainty principle was only hinted at by Bohr, but not really understood early on. Then in 1925, Heisenberg discovers the first formulation of quantum mechanics. Yep.
How would you compute the Bohr radius with the uncertainty?
Well, when delta x gets smaller, then the delta p grows. Imagine for a moment that delta x is very, very small, like 10 to the 20 meters. Of course, at that point, the electron would be far inside the proton. But let's just say we're talking about a positron and an electron. So there's nothing it would go into. Let's say it was 10 to the minus 20 meters or so. In that case, the momentum would be tremendous. The momentum uncertainty is tremendous, so the momentum fluctuates a lot. And you can calculate now, well, if you have your electron there, so close to the positron, like 10 to the minus 20 meters, and it has a momentum fluctuation of the corresponding size, h bar over delta x, you can calculate how far away it can take your electron now. See, so you have the initial position of it, you have the initial momentum of it, and now it works its way out towards infinity against the potential that tries to trap it. And you can calculate how far it takes it. And it will take it very far out. Now, if you do this calculation and you leave the delta x open, and you just calculate for which delta x is the delta p sufficient to make it go only as far as delta x itself is, then that's the Bohr orbit. I mean, up to prefactors of order 1. So in 1925, Heisenberg discovered non-relativistic quantum mechanics. And the key finding was, and I'm mentioning that in this way because for quantum field theory, it'll be a similar story. Heisenberg discovered that the equations of motion stay unchanged when you go from classical to quantum mechanics. For example, a harmonic oscillator is governed by this equation classically, but also quantum mechanically. What makes the theory quantum mechanical is the additional assumption that the positions and the momenta don't commute, but instead we have the canonical commutation relation. Schrödinger discovered quantum mechanics independently half a year later. And of course, what he came up with was the Schrödinger equation. At the very beginning, it wasn't clear whether this quantum mechanics is the same as Heisenberg's. But Dirac, in the same year, showed that the two formalisms are the same. Now, Schrödinger's equation is very popular in first courses of quantum mechanics because solving a quantum mechanical problem simply boils down to solving a particular partial differential equation. But conceptually, I think the Heisenberg formulation of quantum mechanics is somewhat cleaner because you keep the canonical commutation relations. And all the quantumness arises, you can then see that all the quantumness arises because of the commutation relations. And whenever h bar can be seen to be small, you can assume that they are effectively as if they were commuting, and so classical mechanics in some regime can usually expect it to be recovered from quantum mechanics. Not always, there are macroscopic quantum effects, but generally. Now, quantization implied fundamental changes. The fact that the x and the p's don't commute anymore meant, most importantly, that the position as a function of time and the momentum operator as a function of time could not be number-valued functions. They had to be, well, operator-valued functions. In fact, it's even more dramatic than this. Not only can the x and the p no longer be number-valued, because if they were number-valued, they would commute, but also they cannot be finite-dimensional matrix valued, which would be perhaps nice. Remember that in the Dirac equation, you know how the gamma matrices come up, and they can be 4x4 matrices, but the x and the p's cannot. We have to make the jump from number-valued functions to infinite by infinite matrix-valued functions. And to see this, let's just consider the possibility that the x of t and the p of t could be represented as finite-dimensional matrices. So let's say x and t and p of t are n by n matrices, where n is some finite number. Then let's take that equation here. Commutator is equal to I times h bar the identity, and take the trace of it. Let's take the trace of the left-hand side and the trace of the right-hand side. On the left-hand side, we have the trace of the commutator of two matrices. On the right-hand side, we have the trace of I h bar times the identity matrix in our now finite-dimensional Hilbert space. It's just n by n, the Hilbert space is just n-dimensional. But you see, the right-hand side is the trace of the identity matrix, which is the dimension of the Hilbert space, times I h bar. On the left-hand side, we have 0, however. And that's because the trace of x times p is the trace of p times x. It's just the cyclic property of the trace. So we would have that 0 is equal to I h bar times n. That's badly wrong. And in fact, if we increase the number of dimensions in the Hilbert space, it doesn't help, it makes it worse. Because then we have 0 equal to an even larger number there. So what we need is that x and p are represented as non-commuting objects which do not have a finite trace, so that that argument cannot be made. And of course, as a consequence of the non-commutativity, you all know that there is the uncertainty principle, which takes this form, which implies that there are so-called quantum fluctuations. We will go through rather similar arguments with quantum field theory, except that then it won't be the positions and the momenta that are fluctuating. Maybe just to get to that punchline here, a key insight of going from classical to quantum mechanics was, therefore, that uncertainties can be a part of nature. It used to be thought that uncertainties always meant ignorance, always meant, well, things go one way or the other, but maybe we don't know. Maybe we didn't measure, or we measured and forgot, or we lost the record of it. But what this shows is that uncertainty can be a property of nature. Now that was 1925, but very soon after that, non-relativistic quantum mechanics, that is to say, these commutation relations with these equations of motion, became unsatisfactory themselves. And the reason is that that non-relativistic quantum mechanics was not consistent with relativity, especially not with special relativity. And it's not that they were able to accelerate cars or planes to anywhere close to the speed of light, but electrons naturally travel very fast. For example, the electron in the Bohr orbit of a hydrogen atom has already about 1% of the speed of light. So if we treat it with non-relativistic quantum mechanics, just the Schrödinger equation, we should expect significant effects, significant deviations, just because of special relativity. And an accuracy of 1% is very poor for spectroscopy. Spectra can be measured with enormous accuracy, and even 100 years ago, they were able to do so. So therefore, attempts were made to upgrade non-relativistic quantum mechanics to make it consistent with special relativity. This led, on one hand, to the Dirac equation, and on the other hand, to the Klein-Gordon equation. We will not cover the Dirac equation much in this course. I may mention it a few times, but we will not really focus on it. But we will work quite a bit with the Klein-Gordon equation. Can I just ask, who of you is, are you all familiar with the Dirac equation and the Klein-Gordon equation? Everybody seen that before? Maybe not everybody. Okay. Yeah, I will not assume that you have much experience with those. Now, the Dirac equation and the Klein-Gordon equation had some success, but they suffered from serious fundamental problems. It seemed that when you simply take the Schrödinger equation and make it covariant, then the energy is no longer bounded from below. You get a Hamiltonian that has a spectrum that's not bounded from below. This would describe a universe that's not stable. Particles could go through some processes which make them drop into a more and more negative energy state, while, because of energy conservation, releasing a lot of radiation, or a lot of heat, or a lot of energy anyway. And that would mean that the whole universe would be unstable against explosive action without any bound. Also, it wasn't clear whether the unitarity of time evolution was still preserved with the Dirac and the Klein-Gordon equation. And while quantum mechanics, also in the special relativistic formulations of Dirac and Klein and Gordon, allowed people to calculate the scattering of particles of another, there was this curious phenomenon that particles could be created and annihilated. And that could not be described by the Dirac equation or the Klein-Gordon equation. Basically, the Schrödinger equation says that if you start with n particles, you'll end up with n particles. But nature is not like that, and they knew it at the time. Particles can be created and annihilated in scattering processes, for example. And so a new idea was needed. And this last process in particular is a fundamental shortcoming. You could imagine a tinkering, or it was clear at the time, or they thought at the time, that with some tinkering, you might be able to make the energy bounded from below. Dirac came up with the idea of the Dirac sea. Unitarity might be possible to solve, but then they didn't know how to localize particles. But the final problem, namely how to describe the creation of new particles, or how particles could lose their existence. For example, an electron and a positron might annihilate, and then there are two photons coming out. Such a process simply, well, there was no way that you could describe that within ordinary quantum mechanics, relativistic or non-relativistic. So a new idea was needed, and that was the idea of second quantization. It goes back to Heisenberg and others. The idea goes back to a simple observation of Heisenberg. He said, look, in quantum mechanics, everything is subject to quantum fluctuations, and therefore everything is subject to uncertainty, to quantum uncertainty, except for one thing. And that is the wave function itself. The wave function itself is completely deterministic. Namely, just like in the older classical theories, such as the Maxwell equations, when the wave function, when a wave function's equation of motion and the initial conditions are known, then you can calculate what the wave function is going to be later on without any uncertainty. That's very much classical. It's just like a sound wave propagating. So Heisenberg's idea was that one should quantize again. One should quantize the wave function so that it too would be quantum fluctuating. Since everything else is quantum fluctuating, why not the wave function as well? So he played around, I mean, he and his collaborators started playing around with this idea. So they said, the position operator, when differentiated in time, gives you the momentum operator up to a prefactor. And so they thought, well, what if we introduce a partner to psi, which is just like a partner to x. So x has as its canonically conjugate partner p, which is x dot. And if you have several position operators, then you get several momentum operators. Here, the psi, the wave function, well, there are a lot of amplitudes. For every position x, there is a psi of x. So they thought, let us introduce for every psi of x, its time derivative as its canonically conjugate variable. In fact, in classical mechanics, this had been done already. It's just the usual Hamiltonian, classical Hamiltonian formalism for fields. So they said, let us consider the canonically conjugate momentum to the wave function. And then, just like in first quantization, we have non-trivial commutation relations between the x and the p. What happens if we second quantize quantum theory and require that the psi and the pi also have non-trivial commutation relations? So these equal time commutation relations, remember that they are always taken at equal time. I mean, in the Schrödinger picture, you don't have to specify that because x and p are not time dependent. But in the Heisenberg picture, you have to specify at what time you're calculating the commutator. And these canonical commutation relations of Heisenberg are really equal time commutation relations. So Heisenberg and the other fellows thought, okay, let's see. What if we impose equal time commutation relations between psi and pi that are just a copy of these, basically? Instead of the label I and the label J here labeling different positions and their canonical momenta, we now have a label X and a label X prime. So for every X, we have a psi hat. For every X prime, we have a pi hat, just the same way as we have for every I an X, for every J a P. And then here we have a Kronecker delta Ij, but for the fields, we would have a Dirac delta of X minus X prime. So that this thing is peaking when we have x equal x prime, which is to say that this is the canonically conjugate variable to that one. And the overall idea was that while we implement these commutation relations between the field and its canonically conjugate field, we keep the equations of motion the same, just like Heisenberg originally did. Let us keep the equations of motion for psi and pi as they are originally, but on top of that, these commutation relations are required. Now that had a lot of success. The problems with energy positivity, unitarity, and so on were found to be solvable. But then there were a lot of consequences followed directly from that ansatz. Mathematically, it meant that the wave function psi, or let's call it the field, in second quantization it's just called the field, no longer the wave function, the psi and the canonically conjugate pi, then of course can no longer be number valued. This means that the usual interpretation of quantum mechanics, or first quantized quantum mechanics, goes out the window, right? Ordinarily, we take the wave function's modulus squared and it gives us the probability for something to happen. But this thing is no longer number valued, neither is that. So that's both a mathematical and a physical problem. Also, well, in particular, since they are no longer number valued, well, where do they take their values? Well, they have to be operator valued now. They have to be operator valued functions of space and time. And the argument that I gave you earlier for why the x and the p cannot be finite dimensional matrices, because there's an inconsistency with a trace, that argument gets even more stringent in this case, because now we have here a Dirac delta instead of a Kronecker delta, which makes the right-hand side even worse. And it turns out that as a consequence, not only will they not be number valued, strictly speaking, they are also not operator valued. Instead, only if you smear them over some region of space, then they become operator valued. Fortunately, that subtlety doesn't usually impact the calculations. You can usually just work with the assumption that the psi hat and pi hat are operator valued functions, even though in principle you have to smear over them. And that's basically because they are operator distribution valued functions, and you can work with distributions pretty much like you can work with functions. Also, really, one has to be careful there. All right, so the program then is to implement the canonical commutation relations here, and in some way, and to keep the old equations the same, such as the Schrödinger equation, the Klein-Gordon equation, or the Dirac equation. You just keep them exactly as they are. For example, you could just keep the Schrödinger equation, I d by dt psi equal to h psi, just keep it entirely as it is. But on top of that, implement those commutation relations. That's what they tried initially. Well, then we obtain an uncertainty principle for that kind of physics. Now we have an uncertainty principle where there is a bound on the product of the variances of psi and pi. It looks pretty similar to the ordinary uncertainty principle, but notice that this is a Dirac delta here, and this is where it starts mattering then. that this is a distribution, and therefore that you have to really smear over the psi and smear over the pi in order to get a sensible uncertainty principle. You can calculate for, so you choose a smearing function such as a Gaussian, smear your psi, smear your pi, then calculate the commutator between the two smeared functions, and that will determine what the right-hand side is, and it will in general be finite. We will do these things later in this course in all detail, of course, because we want to calculate quantum fluctuations in cosmology. Yeah?
A bit of a tangential question. We second quantize to be compatible with special relativity, and we know that we have trouble compatibility between quantum field theory and general relativity. Do we, potentially third quantize quantum field theory, say by making X and T operators that don't commute with phi and pi or something like that? Because the field would affect space-time. I'm just
third quantization and nth quantization has been proposed, of course. It's very difficult, though. Already conceptually, it's very difficult. I will make some comments about how one can go about this later on when we do these things more explicitly. I definitely invite you to consider it. Maybe, maybe it leads somewhere. Would be great. But yes, you're right that second quantization is not necessarily helping with special relativity. It's a different issue, right? You could do second quantization of just the Schrödinger equation. Doesn't help making it relativistic at all. It only makes it second quantized. Now you can start describing, well, I haven't explained yet why, but this will allow you to describe particle creation and particle annihilation, for example, even though it's not yet consistent with relativity. But if you do this for the Dirac equation or for the Klein-Gordon equation, then you have a relativistic theory which is also second quantized. Yeah, and do remind me on occasion on the third quantization and so on when I talk about second again. Okay. Oh, right. Yes. I wanted to explain why it is that with second quantization you can describe the creation and the annihilation of particles. Remember that in quantum mechanics, in first quantized non-relativistic quantum mechanics, the wave function is normalized to 1. And that's because the probabilities for finding a particle have to sum up to 1. Which is to say, if you're looking for a particle, or that particle, it's like just one particle quantum mechanics, then it's got to be somewhere. Which is to say, you may lose track of it, but it's going to be there. And it's not going to be 2 particles, it's not going to be 0 particles, it's going to be 1 particle. The normalization of the wave function can be interpreted as saying there's 1 particle. But what we have here is that the psi itself is fluctuating. It's now a quantum operator, which means there is no way to normalize such a wave function. What happens to that normalization? The particle number can itself now vary. I mean, it's just a very vague argument here, but we will later see that it is indeed the case that a second quantized theory allows you to describe the creation and annihilation of particles. Also keep in mind that I'm giving you here a historical introduction to how quantum field theory was arrived at. Actually, you don't have to go that way from first quantization to second quantization. You can also jump right into second quantization, which is how usually quantum field theory is introduced. But I think it's nice to think of it historically as well to see how it evolved. Basically, quantum field theory need not be thought of as the second quantization of first quantization. But historically, that is how it happened. So new phenomena are predicted. And what do they describe? Well, there are new phenomena now predicted in second quantization for particles, and there are new phenomena predicted for fields, or for the wave functions. As we already said, second quantization allows for particle creation and annihilation. In fact, it predicts it. It necessitates it. Also, in second quantization, it becomes natural to handle antiparticles. In fact, antiparticles ensure that the theory stays unitary, and they are crucial for compatibility with special relativity. Basically because virtual particles, you probably have heard of virtual particles, can propagate also faster than the speed of light. That is not to say that information can travel faster than the speed of light, but in principle, virtual particles can travel faster than the speed of light. It's a phenomenon of the entanglement of the vacuum, if you like. Now, because particles, namely virtual particles, can travel faster than the speed of light, it means that for a suitable observer, the emission and the absorption process happen the other way around. So instead of a negatively charged particle traveling one way, this observer will see a positively charged particle traveling the other way. In quantum field theory, all of this is nicely built into the framework. But it comes out of the framework, really. Regarding fields, second quantization implies, because of the uncertainty principle for the fields, for phi and pi, it implies that even in the lowest energy state of the theory, which is to say, even when there are no particles, even in the vacuum state, the statement that we don't expect any particles to be seen, so the vacuum expectation value of the field is actually 0. Even when that is the case, then we should still expect that if we were to measure the field nevertheless, so let's say this could be the electric field. Let's say we are in a state where the electric field is on average 0, then because there's an uncertainty principle at work, we should expect that if we measure the electric field nevertheless, we find some electric field. Just like for a harmonic oscillator in the ground state, the position expectation value is 0. When you actually measure where the oscillator is, it's generally not at 0, it fluctuates about 0. And so similarly, the field amplitudes should be fluctuating about 0 even if the expectation value is 0. And that's true in first quantization for x and p, and in quantum field theory, in second quantization, it's true for psi and pi. And for example, just to give you some intuition, in electromagnetism, the role of the Q and the P are played by E and B, the E field and the B field. So even if you have that both the E field has an expectation value of 0 and the B field has an expectation value of 0, then because of the uncertainty principle between the E and the B, because they happen to be essentially canonically conjugate to each other, you have fluctuations in E and fluctuations in B. And you can measure them. You can actually, this is not a measurement, this is just a simulation of those quantum fluctuations. But they can actually also be measured. There's an apparatus called a quantum homodyne detector in quantum optics. And with that, you can actually measure the quantum fluctuations of the electromagnetic field in the vacuum. It's being used already to generate quantum random numbers. You could also use radioactivity, of course, but if you want like a megabyte of random numbers a second, then you don't really want to handle a radioactive source that gives you that many. But quantum fluctuations of the vacuum can do that in a safe way. So there are two main uses of quantum field theory. one main use of quantum field theory is for the standard model of particle physics. And the other, which comes up in the next slide, is for the standard model of cosmology. This is the standard model of particle physics. We will not cover much in this course. In this course, we will introduce quantum field theory for the purpose of the standard model of cosmology. Anyway, let me tell you a little bit about what you're missing. Okay, so the standard model of particle physics, when you apply second quantization, that is to say quantum field theory, that's the second, they are synonymous. Second quantization, quantum field theory are the same thing. Then when you apply that to particle physics, then you're describing the electromagnetic force, the weak and the strong forces. For example, you might have an electron coming in, electron going out, a quark going in, a quark going out, and this electron and this quark are interacting with each other through the exchange of a virtual photon. Or you might have four gluons that interact with each other as part of QCD, quantum chromodynamics, which is the theory of the strong interaction. These would be lowest order interactions, but you also have higher order interactions where, for example, in this process here, you might have that this virtual photon that establishes the interaction between the electron and the quark, this virtual photon might pop into two particles. It could pop into an electron-positron pair, which then annihilates again into a photon, which then establishes that interaction. And there are higher order effects to that. For example, this electron might emit a photon and then reabsorb it again, and so on. Quantum field theory, therefore, becomes very messy very quickly. These processes are calculated quickly enough, but this becomes much more messy because of the integrations involved in such loops. Each loop, each so-called cycle, involves integrations. 4 integrations, actually, for the 4 directions in space or in momentum space. The physics of these loops, of these virtual processes, is that of so-called screening or anti-screening. You can think of it this way. Let's say you have this electron coming in and this quark coming in. The end effect is, the end result is that they will be scattering off because there's an interaction between the two. Now that process is simple, but you see, to higher order perturbation theory, you have to take that process also into account. It's less likely to occur, but still occurring. And it's a process in which temporarily there was an electron-anti-electron pair. And you could imagine that this electron-anti-electron or electron-positron pair provides something like a charged medium in here. I mean, this is just 2 of them. But of course, to higher and higher order, you have more and more of those bubbles. It's as if the interaction between those 2 charges were happening in a polarizable medium, because those electrons and positrons, they will be interacting with these charges too. In higher orders, you can see how they can exchange photons. So what happens is that to higher order, the particles scatter off each other as if they were living in a medium. And you can actually describe a medium with the same methods. If, for example, you have 2 electrons that propagate through a crystal, then they will also interact with each other through the exchange of a photon. But those electrons will also interact with the crystal, of course. And the photon that they exchange will also interact with the crystal. And it turns out that the effect of a crystal on 2 interacting electrons, 2 free electrons, conduction electrons, the effect of the crystal is that the electrons in effect are as if they are a bit heavier than natural, than in vacuum. They might be 5 to 10 times heavier or so. And also the charge can be screened because of the polarizability of the crystal. That's all measurable and describable, and there's a beautiful theory for it. And it turns out that in the vacuum, the same thing applies. Even without a crystal, you have polarizability of the vacuum. And that leads to the phenomenon of a screening of charges because of the polarizability of the vacuum. It turns out that in some theories, such as QCD, you have anti-screening. Now, screening meant that if the two charges are very far away from each other, then they don't see their full charges because the polarization in between is screening it off. You know, the negative charge being drawn towards that negative, to that positive charge, the positive being drawn to that negative charge over here. Whereas if you take the two particles very close to each other, then there is less space in between for vacuum polarization to occur, so they see more of their charges. It has nothing to do with the force being stronger at shorter distance. It's an effect on top of that, whether or not the charges are screened or not. So what we have is that with the usual screening, we have that the charges become effectively, or the coupling becomes effectively stronger as the two charges are put closer and closer to each other. But for QCD, it turns out that the photons self-interact, namely the photons of QCD are gluons, they self-interact, whereas photons don't self-interact directly. And this has, in a way that is not intuitive to me, and I'm not sure if it's intuitive to anybody, it leads to the phenomenon of anti-screening, which is that the charges the coupling between two charges, between two strong charges, between two quarks, for example, becomes the weaker the closer they are, and the stronger the further away they are. So that's one of the implications of second quantization for particle physics. Then other implications are that, I should say, before I get to that, I should say that this is a jungle as far as the math is concerned. It's hellishly complicated, and to calculate higher order perturbation theory is very difficult because it involves so many integrations. And those integrations, to make things worse, and you probably are aware of that already, those integrations often come out infinite. So you have to truncate them and take limits at the end. And this is this program of renormalization that this is the program of renormalization that is needed for that purpose. It turns out that when the force carriers, such as the photons and the gluons, have themselves mass, then this renormalization program seems to be in trouble. But the weak interaction is mediated by particles, the W and Z bosons, which, unlike the photon and unlike the gluon, have masses. How could that be? Well, there's another phenomenon that comes up in second quantization for particle physics, which is that particles that fundamentally do not have mass, and the W and Z bosons fundamentally, in principle, do not have mass, they effectively acquire mass at low energies by a process called spontaneous symmetry breaking, which takes too long to explain in a few minutes. But the basic physics behind it is simply that of a quantum system where the ground state has less symmetry than the action of the system. So for example, if this is a potential, then that potential has complete left-right symmetry. But now consider a ball rolling on that. Well, in its ground state, it's got to be somewhere. That point would not be stable. This would be stable. That would be stable. So any one of those two ground states is eligible. But whichever ground state the ball ends up in, it's not going to be symmetric. It's not going to be left-right symmetric. So we can have a situation where the ground state of the system has less symmetry than the action of the theory, and that phenomenon can explain how particles that in principle have no mass, have a complete symmetry at low energies, behave as if they had mass. And that's, of course, the famous Higgs mechanism that was recently confirmed by the discovery of the Higgs particle that's responsible for that potential, for that kind of potential. Another phenomenon that comes up in quantum field theory, in second quantization when applied to particle physics, is the effect that quantum fluctuations can reduce the symmetry of the action itself. Here, in spontaneous symmetry breaking, we had that the action may have left-right symmetry, but the ground state may not. Anomalies are one step further than that. There you have a classical action which has a certain symmetry, but when you quantize the theory, the action no longer has that symmetry. The quantization can introduce extra terms into the action which do not respect the symmetry. The phenomenon of anomalies is mostly useful for guessing extensions of the standard model of particle physics. There are many ways that in the past the standard model could be extended, but a good guide for how it ought to be extended is the avoidance of anomalies. Because if anomalies arise, then again renormalizability is in question. So you see there is a lot of colorful action when you apply quantum field theory, second quantization, to particle physics, to the standard model of particle physics. How about the standard model of cosmology? And that's the aim of this course. Here we are applying classical general relativity to quantum field theory. Of course, we would like to combine general relativity with quantum field theory, but that hasn't succeeded yet. What we can do is we can combine classical general relativity with quantum field theory. And by that I mean accelerations, gravity, curvature, horizon, singularities. All those things can be built into quantum field theory, where this is a classical background. So we have a classical black hole as a background, for example, or we have a classical expanding spacetime as a background. Actually, we can go a little bit beyond it. We will, in this course, also quantize gravitational waves. And gravitational waves truly are degrees of freedom of general relativity. We will quantize those. That is possible because gravitational waves behave pretty much like electromagnetism does. It's just a linear wave equation. None of the nonlinearity or full general relativity is in there. And it turns out that this quantization of gravitational waves is essential for the standard model of cosmology. And one of the biggest challenges of observational cosmology now, currently, is to find evidence for the quantized gravitational waves. You may remember 2 years ago when there was this big fuss about the bipolarization in the cosmic microwave background. If that observation had panned out, it would have been the first evidence for quantum gravity in a way, because it would have been evidence for the impact of quantized gravitational waves on the cosmic microwave background. Anyway, we will calculate this, and we will calculate what the relationship between the size, the expected size of the quantum fluctuations of gravity waves versus the quantum fluctuations of the inflaton field and these things. Okay, so mostly we will study accelerations, curvature, horizons, and their impact, the impact of those things on quantum field theory. This will lead to a study of the Unruh effect. The Unruh effect is the effect that accelerated observers will find particles when nobody else sees them. An accelerated detector will click even in the vacuum. And this will lead us to reconsider what is a particle anyway. So we will not in this course study gluons versus W and Z bosons and electrons and so on. We will just use, virtually always, we will use just scalar particles, and we will study how they behave in the presence of accelerations, curvature, horizons, singularities, and so on. Because the main phenomena are already visible with a scalar bosonic particle. And what we will already see in the Unruh effect is that the very notion of what a particle is has to be reconsidered in general relativity. And already, if you just consider acceleration. Then we will cover the Hawking effect. There, the key question that nobody can so far reliably answer is, can nature or can it not destroy information? Black holes would seem to destroy information, but then black holes, because of the Hawking effect, might radiate away completely, and then is what comes out having a memory of what went in? Is nature ultimately unitary? Or can black holes ultimately really shred information, destroy it? And this will be one of our main goals, we will cover cosmic inflation. Here the key question is, where did it all come from? This is about the origin and structure of the universe. I'd say a little bit more about cosmic inflation now, because it'll be a key focus of this course. Cosmic inflation is a key part of the standard model of cosmology today. It's the description of the very beginning and a short period after the very beginning. And the picture goes roughly like this. We will do it in much more detail, of course, but just to give you a taste of it. Imagine in the universe a local quantum fluctuation. As we just said, fields can fluctuate. Second quantization describes how they fluctuate. Imagine a field has a potential, V of phi. Imagine that a fluctuation happens, and those fluctuations happen all the time, everywhere. As I mentioned before, for the electromagnetic field, for example, you can directly measure them with a homodyne detector. So imagine you have, in particular, a scalar field, a field that will be called the inflaton field. Imagine you have a scalar field in the universe, and that scalar field fluctuates. Ordinarily, it fluctuates and just fluctuates back, and then fluctuates another way, and fluctuates, and so on. Just like a harmonic oscillator in a ground state, it will just keep fluctuating. But every now and then, it might fluctuate in a particularly large way. It might have a particularly large fluctuation of phi, which might lead to a local elevation of the potential. Now imagine that this occurs in such a way that the potential is elevated locally, because of the fluctuation, to close to the Planck energy. Not quite, but close to it. And by local, I mean just a few Planck lengths across. Just a few Planck lengths across. If this fluctuation is homogeneous, and we will later see why it has to be homogeneous, so it doesn't have much in the way of space derivative, it's just locally in a little patch, in a little volume, a few Planck lengths across, with a fluctuation such that the energy of the inflaton field happens to be very large, a few Planck lengths across. This is a very rare occurrence, because it's a very high energy that's required and very strong homogeneity that's required, but it may happen, right? If that happens, then this V of phi acts temporarily, just while this fluctuation lasts. It acts like a temporary cosmological constant. It just so turns out that when a scalar field has a large potential, then it enters into the energy momentum tensor in exactly the same way that a cosmological constant would. It leads to positive energy and negative pressure, and equal negative pressure. The Einstein equation then I mean, the Einstein equation then leads to expansion, in fact, exponential expansion. Now, if the fluctuation was small, it will just snap back. But if the fluctuation was large enough, namely close to the Planck scale, then that expansion that's produced by this temporary cosmological constant in that volume, that expansion can take off before it snaps back. The Einstein equation is nonlinear, and things can get, so to speak, out of hand. In this case, out of the universe would grow mushroom-like very quickly, exponentially accelerating a bulge, so to speak, of space-time, which in fact within a tiny fraction of a second, like 10 to the minus 30 seconds, could be as large as an entire new universe, basically gazillions of light years across. Eventually, of course, that energy would tend to fall down again. Any system elevated to potential wants to come down again. So eventually we have V of phi going to 0. Oh, by the way, I should say that while the universe from this patch expands and mushrooms out, it doesn't mean that the V of phi dilutes. It doesn't. There's no energy conservation in general relativity. So the V of phi doesn't get smaller because of the expansion. It gets smaller because the potential just naturally wants to go down. And then that energy that used to be in the inflaton potential goes into something else. It goes into the production of particles. So as this inflationary period ends, namely when V of phi goes to 0, the energy that was in V of phi goes into the production of particles, which means that the universe then no longer accelerates so quickly. It slows down, it's still expanding, but no longer exponentially. And it becomes filled with a plasma. All those particles that now have that energy that used to be in the V of phi. While the universe expanded exponentially, the quantum fluctuations of the field phi were amplified. Ordinarily, when you measure, let's say, the electromagnetic field, you find that the smaller the wavelength you look at, the larger the amplitude of the quantum fluctuations. You're unlikely to find a quantum fluctuation of the electric field of wavelength 2 meters. But if you look at tiny wavelengths, you are more likely to find a quantum fluctuation. But when the universe expands exponentially, then that is no longer the case. And you can have large amplitude fluctuations even with very large wavelengths. It goes back to a classical wave phenomenon. All those things we will cover in great detail in this course. So I'm going very rapid here. There's a classical wave phenomenon. Imagine you have a medium. It's all just classical medium and classical waves. So let's say you have a medium, and the medium is expanding. In fact, it's accelerating. In this way, you can have a horizon. It could be that, for example, the medium is accelerating so fast that two speakers who travel with the expansion can no longer talk to each other. Because while the sound tries to cross the medium is expanding so fast that more distance is acquired because of the expansion than the sound can cover in the same amount of time. So on one hand, we have this classical phenomenon that communication is no longer possible because of the existence of a horizon. You can think of it as, sender A throwing a ball towards B and never arriving at B because the expansion of space is faster than the ball can fly. Now, let's ask, this is the particle picture. What's the wave picture of that? What if you have an expanding medium and waves in there? In this case, the critical length is the wavelength of the wave. It turns out that waves that have a much shorter wavelength than the horizon will just keep oscillating happily. But waves whose wavelength is larger than the horizon, and that's a phenomenon that's even classically true, will stop oscillating. It's just the ordinary wave equation. Ordinary wave equation has this phenomenon that waves of wavelengths larger than the horizon will stop oscillating. They will just keep whatever amplitude they have. And the quantum theory of that is crucial, and according to the current standard model of particle physics, is the reason why we are here. Namely, the quantum field is fluctuating, ordinarily, mostly at tiny, tiny length scales. This is where the amplitudes are large. But the universe expanded dramatically fast with a short, very short horizon size. And that meant that those quantum fluctuations at tiny sizes, just the size of the horizon, had large amplitude, and then because of the expansion were frozen. So they were frozen, and that meant that those large amplitudes that normally only occur at short wavelengths then started to occur also at long wavelengths. So the current standard model of cosmology has it that because quantum fluctuations were frozen at the size of the horizon during the inflationary expansion, the exponential expansion of the universe, when that expansion ended, those quantum fluctuations I think it's just timed out. Those quantum fluctuations imprinted themselves in the initial plasma that the universe was filled with. Then the universe, of course, cooled down, and because it continued to expand, and those initial inhomogeneities in the universe then seeded the condensation of the plasma into clouds, actually after about 100,000 years, on the order of 100,000 years. The plasma became hydrogen because it was cold enough for the protons and the electrons sticking together. And then these inhomogeneities gravitationally attracted each other, and eventually you get the formation of galaxies and a universe that looks like our universe today. So the idea is that the inhomogeneities in the universe today, the reason why there's a galaxy here and not there, the reason for that would be a quantum fluctuation. A quantum fluctuation that started out at a tiny, tiny length scale. The size of the horizon during inflation is thought to have been only about 5 orders of magnitude larger than the Planck length, only 10 to the minus 29 meters or so. And there, quantum fluctuations are large, but they were frozen while the universe expanded exponentially, and so imprinted themselves into the primordial plasma, and later then those over and under densities led to the condensation of hydrogen into galaxies and stars. And so the overall idea is that the inhomogeneities in the universe today can be traced back to quantum fluctuations. This outrageous idea goes back to 1979, 1980. There were Braud, Engler, and Starobinsky, and a few other names, Mukhanov, and so on. Mukhanov, one of the co-authors of that textbook that's on the table here, which we will be following in part during this course. That audacious idea goes back to the early 80s, when it was just one idea out of many to explain the inhomogeneities in the universe today. But it's now the leading theory because, amazingly, the predictions for the statistics of the distribution of galaxies and the statistics of the temperature fluctuations in the CMB matches very nicely with the predictions from that scenario. And how to calculate those we will cover in this course. I should say that the second half of this scenario is what is experimentally very nicely confirmed, and I would say spectacularly. It's a fantastic thing. The first part, though, we cannot experimentally check just yet. The idea that a universe is spawned from a mother universe, a daughter universe is spawned from a mother universe, and then that daughter universe may spawn further universes simply by the occurrence of quantum fluctuations that have an elevated potential on some patch of a few Planck lengths across, is in a way an automatic consequence of cosmic inflation. But it's just that we don't really have good observables for checking whether this is what was going on. So in principle, it could be that the inflation at the beginning of our universe was the very first there ever was. And the reason for the initial conditions may be out there, and we have no idea what they are yet. But it could also be, and this is what in principle I think the theory is saying, is that we don't really need a reason for inflation to happen. It could just happen because of quantum fluctuations. Once you have a theory of a scalar field with a potential, and the potential fulfills some minimal conditions, then the universe won't be stable. It will have, because of the interplay of quantum field theory with general relativity, the feature that such quantum fluctuations can lead to the spawning of a daughter universe. So this is, I think, a beautiful picture, but honestly, experimentally, we have no confirmation for it. But that picture here, namely that quantum fluctuations during the initial exponential expansion of the universe, where what seeded the structure in the universe, that is something that can be calculated and can leads to explicit predictions, which can then be checked in experiment. Okay, so these are the things we'll do in this course. Let me know if you have any questions. Oh, and this is the book. If you haven't filled in your name and email address in here, please do it, and I will set up an emailing list. Please let this go around. And this book here, Quantum Effects in Gravity, by Mukhanov and Vinitsky, is quite nice. We will follow it to some extent, and while it's nicely explaining things, it also has exercises with solutions in the back. Very rare for grad text, but it does have that. So I can recommend it, but it's not required. Any questions? Yes?
This is from, when I use the term redshift for the waves that when the universe was not expanding, was very small before expansion. Let's say we have two observers, one is sending and the other one is receiving. Because they're moving on a corner system, and let's say there's a standing wave of some frequency. Would it be correct to use the term that the wave is being redshifted and eventually the frequency will decrease as the universe expands? But would that be the proper term to use?
Half of it. Yes, it will definitely be redshifted, but the frequency can go to zero right away. You see, the spatial frequency is diminishing, it's getting redshifted, but the temporal frequency goes to zero when it crosses the horizon. And then, and what exactly horizon crossing means, of course, we will cover all that in great detail. And then eventually inflation ends, the horizon will become very large again, the wavelengths become smaller than the horizon, and it starts oscillating again.
So we're going to study how quantum fluctuations and horizons interact. Are we going to try to relate this to black holes?
We will cover black holes as well, but it's sort of separate. We will study the general mechanism by which quantum fluctuations can amplify waves, such as in the case of inflation, or generate particles, it's, Bogoliubov transformations and things like that. And then we will apply that mostly to inflation, but also to black holes. One more thing I want to say is that the course will have a project, not a final, but a project. And the project consists of calculating quantum fluctuations of fields and explicitly simulating it. I mean, talking about the theory behind it, then calculating them, simulating them, displaying them. In the simplest case, just quantum fluctuations in Minkowski space, take a cube, calculate quantum fluctuations. I will explain, of course, exactly how to do these things. And then, and that is a more advanced problem then, once you can do this, then do it for an expanding universe and see how quantum fluctuations get amplified, or not really amplified, but dragged to large scales while keeping their amplitude the same. And this should give you then some intuition. First of all, you know then how to calculate these things, and on the other hand, it gives you some intuition for what's going on. On the website, there's already a description of the project, but I may still modify that description a little bit over the next few weeks. And I'll let you know when the final version is being arrived at. Yes?
What is the uncertainty principle and the general postulates of quantum field theory not Lorentz invariant?
It turns out that second quantization can be made Lorentz covariant. It's just that you don't see it immediately. So you get equations that look as if they were not Lorentz covariant, but all the predictions that you can make are covariant. So it's true that the uncertainty principle doesn't look covariant, but still the quantum fluctuations are. In fact, that will be one of the things that come out of the project, namely that if you plot the quantum fluctuations and you change the perspective, so let's say you go into a boosted frame, you get exactly the same thing. I mean, let's say Minkowski space. Whether you slice space-time this way or that way, you get the same thing. The quantum fluctuations are actually covariant. Yeah, and you can then see exactly how it happens that they come out covariantly. All right, so I see you on Friday.